Adaptive PM for earlier detection of errors on OTN and ASON connections using data mining. Abstract: in large optical networks, there are large number of circuits, connections, rings, provisioned for the increasing demand of connectivity with high speed and service assurance. When we talk about service assurance, we must ensure and prove the quality of service of the large optical networks, which talks about reliability and reliance of the company's service provided to the users. Due to rapid growth in consumers, optical network, which is like a backbone to most of the latest technologies and faster connectivity, is in great demand. Performance monitoring provides a measure to quality of service of such large optical networks. Due to its wide utility, performance monitoring of large optical networks needs to be done extensively. This paper covers how early detection of errors in the OTN and ASON connections can predict the connections with high risk. This will give user an early information about those connections and give ample time for correction. Performance monitoring testing of large optical networks is done in both control and managed plane scenarios. Test bench has more than 5,000 networks elements and more than 3 lakhs paths. Nodes are added in network management system on which network connections are provisioned through automation. We have successfully implemented and tested adaptive PM for earlier detection of errors on OTN and ASON connections using data mining in our lab. Keywords: PM, bin, counters, granularity, termination point. Introduction. Performance monitoring is an important aspect in optical networking. This is the measure of service assurance. Quality of signal is very important as that of communication. Customers need service assurance, which is like guarantee of service. Now question arises, what is PM? PM, performance monitoring, is the ability to perform low-level quality monitoring in the network by counting certain parameters, e.g. number of errors. Why PM? A. Service level agreement, SLA, monitoring. To verify that the service level provided by the network is consistent with the agreement with the customer. B. Fault localization. To find low-level faults in the network. 2. PM terminology. Generally we measure certain events, called counters, for a fixed period of time, called granularity, and store the results internally for some time. Traditionally in transport networks 2 granularity periods are used. 15 minutes, used for fault localization. 24-hour, used for SLAs. Other granularities, 1 hour, immediate. The management system can collect this data, called historical PM, across bins and store them internally, for a certain period. The management system can also request the current value of counter to network element, called current PM. End user can generate reports to visualize/access this data. Monitoring can be considered as a number of different types. Digital PM. Traditional SDH/SONET PM, which counts the number of errors in a received signal. RS, MS, VC4, VC12, etc. G.826, end-to-end error performance parameters and objectives for international, constant bitrate digital paths and connections. Figure 1, digital PM counter on 15 minutes interval. Adaptive PMF. Or earlier detection of errors. On OTN and ASON. Physical layer monitoring in SDH/SONET NES. Optical channel level monitoring in WDM equipment pre-OTN. The data is usually non-zero and the customer is looking for changes in values to identify upcoming failures. Ethernet PM. Mechanisms for monitoring the performance of Ethernet networks. Like digital PM, it is counted, e.g. bytes transmitted, packets dropped. Can be performed both at a port level and at a flow level. No general rules for good or bad values, it depends both on the counter type and customer. For instance, a high byte transmitted for a certain customer may mean they have sent too much data today. 3. Connection and PM counters. Consider the below figure 4. In the above figure 4, we can consider following 4 PM TP, performance monitoring termination point. Node A, NEND, transmit, 15 minutes. Node A, NEND, receive, 15 minutes. Node B, FEND, receive, 15 minutes. Node B, FEND, transmit, 15 minutes. Another 4 PM TP for different granularity, e.g. 1 day. Node A, NEND, transmit 1 day. Node A, NEND, receive 1 day. Node B, FEND, receive 1 day. Node B, FEND, transmit 1 day. In case of a multi-hop connection, PM can be enabled at all the points, figure 5. For functional overview. A typical performance monitoring system does following functions. Manages requests toward the network to activate/deactivate PM. Manages storing for historical PM data collected via the adapters. Manages historical PM data visualization and reports. Manages historical data archiving. Periodically generates PM report to be exported to external OSS. Manages TCA. V-test procedure. Capture the PM files from real setup and use them to mimic the PM files. Write scripts to generate PM files by taking certain inputs like any details on which PM files need to be generated. Different types of PM data have different file structure and hence need to create separate scripts to generate the PM files for analog/F/OCS/SDH etc. 15 minutes and 24-hour PM granularity have different values in PM files. Hence need to take care which script to use for what data types and of what granularity. For 15 minutes granularity, every 15 minutes, PM files should be generated, and for 1 day granularity, PM files should be generated only once in 24 hours. Measure the performance monitoring of the large optical networks by simulating large PM data sets. We have tested with large PM counters in our lab. Test benches having approximate 415K CSV records. Average CSV report generation time is 50-60 seconds. Average load. Average CPU utilized. Average memory used. According to ITU standard G.826, whenever consecutive severely errored second, SES, counters detected on a particular connection, then it may have service impact on it. If the error blocks are equals 30% in a given second, then SES will increase. The formula 2 equals T10 where, for T seconds, if SES persists then it will impact the service severely, which may cause signal degradation and lead to disconnection of services. Hence in our approach we monitor OTN and ASON connections with SES counter values to predict the connections with high risk. With the help of data mining technique, we have correlated different PM databases and sorted the connections with high SES values and presented the data in the tabular form as below. Due to the high SES counter values, these connections are most vulnerable and needs immediate attention. 6 conclusions. Performance monitoring testing in large optical network is achieved with like real transportation system by mimicking the real data which is captured and emulated on thousands of network elements to test large data set. It is good to test performance monitoring on large optical network involving thousands of nodes, lacks of connections, since service assurance is very much required. This performance monitoring test on large optical network demonstrated to satisfaction of the test results. We have detected connections with high risks by fetching the connections based on SES counter values and timestamp. This is achieved through data mining the different DB tables and correlating them with the connection names.